Hello, my name is Jarvis Moorfrost, and I'm presenting a contributed talk on mobility, defect scattering, and vibrational response of Feynman Polarons in Halide Perovskites. So one of the unique features of this class of semiconductors is that they're incredibly soft, and this means that at room temperature, they're extremely disordered. So if you look at the molecular dynamics of this material, you see it's almost like a jelly. The individual atoms are moving off-site by about sort of 40% of the unit cell, and the octahedral network is continuously distorting and rearranging. And this is really disturbing from a modeling perspective, because we almost always assume that there is a representative athermal structure that we can then use for all of electronic structure calculations and sort of downstream device physics. This softness appears in the lattice dynamics as these sort of very many low energy modes which are associated with sort of the tilting and distorting of the octahedra. If we take these eigenmodes and then decorate them with these Born effective charges, which are a quantitative representation of how polar the material is, we can calculate the vibrational contribution to the dielectric constant. And what we find is that this vibrational contribution is really very large. And having a large dielectric constant has enormous ramifications for the device physics of the material. But the particular sort of effect of this dielectric constant, which I'm going to describe in this talk, is that it drives the formation of polarons. So these are actually easiest to understand in this limit of small polarons, which is where this dynamic competition between the kinetic energy of the electron and the response of the lattice is actually capable of fully localizing the electron. So it's just stuck in one location in the lattice. And everywhere else in the lattice, the static dielectric constant responds Fröhlich. So you end up with loads of polarization fields that all sort of point at the electron, and it ends up sitting in this sort of bathtub potential generated by these polarization fields and doesn't do anything basically. Unfortunately, in the hybrid halide perovskites, this is probably not a very good model for what's going on because the effective masses are too small. So basically the kinetic energy can fight more effectively against this very strong localization pressure from the lattice. So to be able to sort of treat this sort of on a more formal footing, it helps to first simplify the problem that you're solving. And so in sort of a typical physicsy way, we go back to sort of a 1950s simplified Hamiltonian, where you have just a single effective mass electron, and then you have your infinite field of boson excitations within the lattice. You can parameterize this Hamiltonian from doing electronic structure calculations. And one of the nice things about using these sort of effective theories is you can actually take the different parameters that you use to get this overall electron-phonon coupling, this alpha parameter, from whatever theory gives you sort of the most accurate results. So in the rest of this work, the optical dielectric constant and the effective mass, we're going to take from QSGW calculations, and then just sort of the bulk phonon response, which gives you the static dielectric constant and the phonon frequencies, we take from simple density functional theory calculation. And in the case of the halide perovskites, we end up in this sort of unusual intermediate regime. So the alpha parameter is about 2.4. And in comparison to other sort of even quite polar semiconductors, such as cadmium telluride, it's much larger. But when you compare it to things such as the oxide perovskites, such as strontium titanate, it's quite a bit smaller. So we're really in this intermediate regime between something which is probably well described as sort of block waves and sort of plane waves, charge carriers, and then this other limit where you have sort of fully localized small polarons. So this Hamiltonian looks quite innocuous, but it's quite difficult to solve. And the big problem is that you have an infinite field of the boson excitations. So it's only a single effective mass electron, but you need to consider both the thermal population of phonons and all the sort of creation and annihilation that can go on, and any sort of possible combination of Feynman diagrams that you need to consider. And as a quantum field problem, it's one of these areas where the path integral formalism of quantum mechanics is actually quite powerful. And there's this famous paper from Feynman from 1955, where he used a variational technique where you take the Lagrangian representing that Hamiltonian, which we can't solve exactly, even with path integrals, and you match it up to a more simple Lagrangian, this one that actually represents sort of almost a quadratic term that couples between the electron and the phonons. And you minimize the mismatch between these actions, and then that gives you the quasi-particle state. And it's really quite literally a quasi-particle, and in particular you can interpret the equations of motions once you solve for this as your effective mass electron coupled via spring coupling constant K to an additional mass, which represents the phonon drag term as you sort of go around the lattice. And so there are tabulated values for this in the literature, and you can find textbook expressions, but they all make the assumption that you're in the low temperature regime. And low temperature in this case means relative to the phonon energy. So of course, because this material is very soft, you're explicitly in the high temperature regime already at room temperature. So we went back to these sort of papers from the 50s and 60s and wrote our own codes to explicitly solve this variational problem and do all of the integrals numerically rather than take these sort of low temperature approximations. One of the main things that you can do with this model is to calculate a mobility theory. And so a lot of the mobility theories that you see in the literature are all actually based on this classical theory of the Drude model, where you just have electrons sort of pinging around between the atomic cores. It was slightly patched up to make it more sort of consistent with quantum mechanics in the 20s, but really fundamentally it's a semi-classical model. So even very sophisticated studies that you find in the literature, which go to a lot of effort to calculate all of these matrix elements, then take these matrix elements and then just put them into a simple semi-classical model. With the Feynman Polaron state, however, there was some additional work in the 60s, which actually gives you a full quantum mechanical theory of mobility. And there are still limitations in this, of course. It's only a linear technique, for instance, but it does include all phonon scattering processes up to all orders. And just as a comparison, recently there have been these studies with diagrammatic Monte Carlo looking at where the semi-classical theories of mobility break down. And really all I'm showing here is just the Feynman technique on the left-hand side, and then these sort of really quite sophisticated recent calculations on the right. And you see that you can reproduce the same sort of unusual trends, both as a function of temperature and as a function of frequency. So you see these sort of quantum mechanical resonances in the mobility theory. And so applying this for the case of methylammonium-lead halide perovskite, about 3 years ago, we got these sort of nice smooth curves, which of course are the model data. And at the time, these compared quite well to a couple of room temperature single crystal data points, and then this temperature-dependent data on a polycrystalline sample when the mobility was quite a lot lower. At the time, people were very interested in looking at the sort of the exponent of how this mobility drops off in a log-log plot, because this can be used as circumstantial evidence as to what the dominated scattering process is in the materials. And so again, this is the sort of the smooth theoretical data and then the actually observed experimental data. And there the exponents were quite different, really. Depending on how you fitted them, the exponent on the experimental data was between about -3/2 and -1, whereas the theoretical data gave a very clear suggestion that the exponent was about -0.5. However, this measurement was followed up a year later in a sort of a similar material system in the form amididium-lead triiodide. And what they observed there was a sort of a decay of the mobility as a function of temperature, which matched almost perfectly with the sort of the Polaron theory, and an overall actual value of the mobility, which is fairly consistent as well. So you get a lot of other sort of information out of these mobility theories. You know what the effective mass renormalization is, and you know what the scattering constant, and you have some idea of what the Polaron state is in terms of how localized it is within the lattice. And combining these together, one question is, how do Polarons scatter? Because usually when we have sort of device physics like expressions, they all sort of eventually, if you sort of follow them down through the literature, become based on the Born approximation, which assumes weak scattering and that the input and output states of the charge carrier state are plane waves. So what happens when you've localized into a Polaron state? Well, luckily, this problem has come up in the context of accelerator physics before, and essentially just by reproducing their derivations but taking the opposite limit of whether when you're at low speed rather than close to the speed of light, you can get an expression for what the scattering cross-section of polarons versus electrons in this lattice should be like. And so here the orange curve is if you had a plane wave state, which is usually what's assumed, whereas if you include the fact that you've localized to a polaron, you massively reduce the cross-section, and you also mean that you can only scatter very small angles. And there's two separate contributions here, as well as the obvious one of just the dielectric constant. There's a classical contribution because you've actually localized the electron, therefore it's less likely to hit stuff, basically. And then there's an explicitly quantum contribution because your Gaussian wave packet is actually incoherent, and so you can't interfere positively to scatter backwards on itself. And if you wait for this for transport, the effect is actually even more severe. So finally, as well as the phonon modes renormalizing the effective mass and the behavior of the electron, it's actually normalization is always a two-way door. So the interaction via the electron-phonon coupling with the electrons will also renormalize the phonons. And again, the Feynman theory, you can directly get these values just out of the theory. This sort of ball and chain obviously does simple harmonic motion. And what it should produce is a series of resonances at a multiplex of the phonon frequencies. So if you take all of this information together and put it all in, what you should actually be able to see if you look just below the band gap of the material is you should see the bound polaron state, so bound in total by about an energy of about 23 millielectron volts. And if you were to look at the coherent excitation of the state, you should be able to see energy exchange between the polon, the electron, and their renormalized phonon degrees of freedom as the energy sort of passes backwards and forwards. And as you excite closer and closer to the actual band edge, you're basically going into a less and less well-bound polaron state until eventually all of this stuff just disappears and the energies just go to zero. And this data actually compares really quite well to some unpublished data, which I saw from XYZ's group. So finally, in conclusion, halide perovskites are soft and polar. The Feynman Polaron theories seem to be a pretty good model for the correct physics, and we can use them to predict temperature-dependent mobilities, reduction, defect absorption, and cross-section as a result of the polaron state, and the renormalization of phonon energies. And also additionally, though not described here, we can go some way to describing the observed slow carrier cooling in these materials. So finally, just as acknowledgements to EPSRC and Royal Society for funding. And a lot of this work was all started when I was a postdoc in Aaron Walsh's group, and it's all been developed in collaboration with experimentalists, in particular Piers Barnes, Artem Backlin, and Tom Hopper. So thank you very much for your attention.